When we think about solving absolute value inequalities, we have to extend our thinking from yesterday's lesson on absolute value equations. Starting simple with the absolute value of x is less than 3, we might want to make an IO table with true-false as our outputs to decide which values on this number line might be true and which would be false. We'd probably come up with something like this, where numbers in the middle, from say 0, 1 and -1, 2 and -2 would be true, and yet 3, -3, 4, and -4 would make this inequality false. So we'd start by graphing an unshaded point at +3 and -3. And then, because the in-between values are true, we would be shading in between, much like an AND in a regular compound inequality. On the other hand, if we wanted to solve the inequality, the absolute value of x is greater than or equal to 3, then we would make another true-false input-output table that would look similar in the inputs but exactly opposite in the outputs, where the in-between values in this case are false, and the outer values, where the absolute value of numbers gets further and further away from 0 and therefore larger, will be on the outside. Those are the true values. So this time we're going to use a shaded in point on 3 and -3, and we're going to shade from 3 all the way towards positive infinity, and then from -3 towards negative infinity. So if we were to summarize what we just did, we can change an absolute value inequality into a compound inequality in the following manner. If we are solving a greater than or equal to or greater than absolute value inequality, then we need to be thinking about an or compound inequality. On the other hand, if we happen to be solving a less than or equal or less than symbol, then we're going to be thinking about a less than compound inequality.